let's start with an example of taking a ball at ground level and throwing it up into the air so that it goes to some height. We know, of course, it will fall back down to Earth. And as it goes up, its kinetic energy, which is a function of its velocity, decreases as it slows down until it gets to the highest point, and that's where the potential energy, the gravitational potential energy, will be the most, and the kinetic energy will be the least, and then it'll start coming back down, and as it falls back to the ground, the potential energy decreases and the kinetic energy increases. Usually, we choose the ground to be our reference point for potential energy, and we say the gravitational potential energy down here is 0, but that is very arbitrary. What if we chose instead to let this point way up here be a height of 0? Then all the other locations would have a height that is below that level, which is indicated by the negative sign. And so just for simplicity, I'm letting g equals 10 instead of 9.8, and I'm letting the mass of the object be 1 kilogram, so that our calculations for potential energy and kinetic energy are much simpler. So that means up here, if this is my 0 height, that means when the ball is at its highest place, its potential energy is 0. But that's also where it is not moving, so its kinetic energy is 0. So that means my total energy in my system is the kinetic energy plus the potential energy, or 0 joules. So anywhere below that now, yes, the ball is moving, but the potential, so it'll have a kinetic energy, but the potential energy will always be negative. And that's a key idea here that we're going to extend to when we talk about gravitational potential energy of objects that are far away from the Earth's surface. You'll see when we get there. We're going to let a very far away location be our reference point for potential energy of 0. And then as the object gets closer to the Earth, we know that as an object gets closer to the ground or to the Earth, its potential energy decreases. So that's what we see over here. The potential energy up here was 0, and now that it's gotten closer to the Earth, the potential energy is a negative value. And as it gets even closer, it becomes a larger negative value. So be careful here. For many of the topics that we talk about, the magnitude indicates a larger value, even though it's negative. For example, negative 10 meters per second squared is bigger than negative 5 meters per second squared. But in this case, that is not true. 0 is the greatest amount, and as we become more negative, even though the magnitude of the number is getting larger, the amount of potential energy is becoming less. You can see that the kinetic energy, I solve for the kinetic energy by saying the total energy equals 0, so the kinetic energy must be the total energy minus the potential energy. K equals 0 minus U. So that's what I've done here, and you see that I always get a positive value for my kinetic energy. Kinetic energy can never be negative. So I can't have a location up here above this spot based on conservation of energy, because if it's up here, that means my potential energy would be positive, and I know the sum of the energies is 0. So if I have a positive potential energy, in order for them to add to 0, I would have to have a negative kinetic energy. So this area up here is off limits. We're constrained by the rules of our system, that the total energy is 0. And this number, remember, is arbitrary because of where we have chosen our potential energy location of 0 to be. Here's the expression for gravitational potential energy of an object of mass little m at this distance away from planet of mass big M. We're going to prove this, but for now I'm going to present it to you. And let's just take a look at what this is saying. Remember, our potential energy, we're going to define it to be 0 at infinitely far away. So that means r, the distance away, if that's infinite, then this number is 0. Okay, and then as we get closer to the planet, r becomes a smaller number, so the magnitude of this fraction becomes larger. But remember, it's negative, and a larger negative number means less potential energy. So as it gets closer to the planet, the potential energy is decreasing. Okay, now let's take a baseball. Let's say we start at some height above the Earth's surface. We're holding in our hand, perhaps, at point P, and we throw it straight up into the air. I know that as I throw it up into the air, its gravitational potential energy increases, and it starts to slow down, and its kinetic energy decreases. Let's calculate how much work is done on the ball by the force of gravity as it moves from point P to infinity. Okay, so we're going to go back and look at our equation from Chapter 7 for a variable force. Is work is equal to the integral of the force with respect to the direction. Okay, so let's do that. From position P, which we'll call at a distance r away from the center of the Earth, all the way to infinity. So those are my limits of integration times of the force with respect to the direction that the force is exerted over. Okay, now I know the force of gravity is G big M little m over r squared dr. And when I integrate that, well, first I'll pull the constant outside the integration, and now I'll integrate 1 over r squared dr. Now I'm plugging in my limits of integration. So this is infinity, so that's 0, minus what I get when I plug in the lower limit. So I get then that the work done is minus gm m over r. In Chapter 8, we learned that a change in potential energy is equal to the opposite of the amount of work done. If you forget, it's not too hard to remember. Just remember, if potential energy goes up, that means the kinetic energy must have gone down, and I know positive work is when kinetic energy is added to the ball. All right, so if its potential energy is going up, that means it must have been negative work done on the ball. Okay, so remember, delta U means the final minus the initial. I'm throwing the baseball upward, so that means my final potential energy is at infinity. The initial position was at point P, and I know by definition I defined the potential energy at infinity to be 0, and we showed over here that work is equal to minus G big M little m over r. So I plug that in, and I solve that for the potential energy at point P is equal to the negative of G big M little m over r, which is what I set out to prove. At the very beginning, I said we were going to show you why this is the equation. So we calculated the work done by gravity on the ball as it moved from this spot here at a distance r away from Earth's center to infinity. But in order to get there, it has to have some initial velocity. If it has less velocity than that, it won't go to infinity. It'll go to some height, stop, and then fall back to the Earth. Just like the saying, what goes up must come down. But if it is to go to infinity, there needs to be some minimum speed here at point P. We call that the escape velocity. And we have to touch on an idea that we learned back when we were talking about gravitational potential energy, and that's path independence. Gravity is a conservative force, so work is only done when there is a displacement parallel to the direction of the force. And if I go perpendicular to the force of gravity, no work is being done. So that means if I want to get away from the surface of the Earth, it doesn't really matter if I go this way or if I go this way, because the distance from here to here is the same as the distance from here to here. And once I'm at this spot, I can get to this spot by going perpendicular to the gravitational field lines. So this path is the same amount of work as this path. So in other words, my escape speed or my escape velocity is independent of the direction that it's moving. Okay, I can begin parallel to the Earth's surface, or I can begin perpendicular to the Earth's surface, and I'll get to this altitude with the same amount of work, neglecting air resistance, of course. Okay. We know that the total energy of the system is the kinetic energy plus the potential energy. So remember, at this point, the total energy is K plus U. When it gets to infinity, that's when the potential energy is 0, and in order to get there, that's where it has to just reach when it runs out of speed. Okay, so that means when I get to infinity, I'll have 0 potential energy and 0 kinetic energy, and that sum is 0. And what is the velocity needed at point P to get out there? So I'm going to solve this equation for V, and I get the square root of 2 times G times big M over R, and that is my minimum speed required to escape Earth's gravitational field, right? If R goes up, that means I'm further away from the Earth's surface, and then I won't have to get it going as fast to get away from Earth, and that's what I see. If R is bigger, then my escape velocity is smaller.